All right, today is another Xanadu quantum codebook. Um, for those of you who like these walkthroughs, then enjoy. For those of you who like the other things that I've done um, more, which is completely fine, um, hopefully I'll get some done early in the new year. I have some ideas for some recent paper replications and some discussions of quantum chemistry, open fermion, etc. But the reason I'm doing these is just over the holiday break, they're really easy. The amount of recording you see is literally the amount of work it takes. If it's a 20-minute video, it took me 20 minutes to do, whereas other ones that require me to write code and check things and go read papers take a lot longer to produce. So these are just easy to get done sort of over the holiday break. But anyway, we'll just jump right into it. So we have Introduction 10. Maybe, hopefully soon we can get done with the introductions. I'm going through these a lot slower than I thought I would. So it looks like we're just talking about expectation values, which we've seen before in the VQE, this exact sort of operation where we're minimizing the expectation value of the Hamiltonian is what we see there. So we just see Hermitian matrices is just saying that the matrix is equivalent to its conjugate transpose, which means that if you need to reverse that quantum operation, which all quantum operations are reversible, then you can just do the exact same gate. So X gates, Pauli gates, Hadamard gates are all Hermitian. Oh yeah, and observables. This is just a general property actually of all quantum operators, as a matter of fact. So even if you think about again, in just normal quantum mechanics, right? You have the momentum operator, you'll have the position operator, you'll have all these different operators, creation, annihilation, whatever. Any operator has to be, any measurement operator, maybe I should specify, has to be Hermitian, because Hermitian matrices eigenvalues are all real numbers. So in some sense, right, now this is, I don't know, to be honest, whether, this is maybe to me a chicken or the egg question. Are all measurement observables in quantum mechanics Hermitian because we can only measure real values? I mean, like, you can't measure an imaginary number. That doesn't make sense. Like, we can't conceptualize what that would be. Like, what is, if I were to measure how many, fractions there are, how many cookies are on the table, it's I cookies, that doesn't make sense. So is it Hermitian because we can only measure real eigenvalues, or are these sort of eigenvalues real, and so everything happens to be Hermitian? I guess this is maybe sort of a realist versus, these different perspectives on the nature of scientific laws, but we don't need to get into that sort of metaphysical discussion right now. So anyway, I got sidetracked there. We have this circuit design that we're working on. We got introduced to a new function, xval, which obviously gives us the expectation value of some observable. So we want to implement the circuit that they give us. So we can do the Rx gate, pi over 4. Once again, it's Hadamard, very annoyingly. I feel like I'm going to make a PR to Penny Lane and just alias it as the H gate. And the Pauli, also it's annoying that I have to type Pauli Z instead of Z, but I'm sure they have design reasons. They're just annoying design reasons. So now we want to take the expectation value of the Y matrix on the qubit. All right. What do you know? Correct on our first try. Excellent. We can also do custom observables using the Hermitian, which creates presumably a Hermitian observable. Of course, these may not be useful for hardware, so that's fine. All right. Wow. qml.math.unwrap. That's wild. Okay. Oh, I see. I thought it was calling some function. Never mind. That's not that interesting. So we want to do this. I'm not rewriting this. I'm going to copy it from up here. So we want to do the Rx, Hadamard. I don't know why I didn't also copy the poly-z, but then we want to do shot results dot append. So we're keeping track of these in an array. qml.xval. The y gate, poly y is equal to 0. But the one difference is that we want to create our device, which we can do here. If it lets me copy it, which it does not. Do I have to run the device? Yeah, see up here it was creating the function, whereas I don't remember how to do this. I have to go back. Let's see. I'm going to introduce us to devices. All right, we see devices here. Oh, right, we have to do. Oh, okay. Actually, we don't have to do it. We can just do this here. I was just thinking about how to best create this. So we can do. Back here, we can do, just copy this. Oh, that's not what I wanted to do. Put this over here. Then we want to do shots equals shots. So we're changing the number of shots. We're specifying the device. And then this should just work. This is maybe not the best way to do this, but you know, it's probably going to work. And that's really all that we need. Shots.append. All right, let's see. What are the odds this works? Yeah, it's probably not the best idea to create functions inside for loops, but you know, it works, so who am I to complain? Yeah, you can see it approaches the true value. It's surprising that that's actually off by so much. 100 shots is usually pretty good. Yeah, so it's just, I mean, that's just what an expectation value is right here. We can sample it directly, so we'll get the ones and negative ones right here. So we'll do qml.sample. What am I supposed to sample? The y observable. And we want to compute the expectation value. So what we want to do is we want to go through, we want to do so we have the number of ones minus the number of negative ones all over the number of shots. So this is equivalent to the average value, right? Because this is going to be the sum of the ones this is going to be the sum of the negative ones, which if we add -1, -1, -1, then we get the results. So what I think I can do here is just do this. Yeah, all we're doing is taking the average value, so don't need to do anything fancy down here. Don't even worry about that formula. All right, what are we doing in this one? Explore how accuracy of the expectation value depends on the number of shots. So if we run lots of experiments with high variance, how does that look? I guess we will find out. Create a device with the number of shots. I'm just going to go up here and do this again. I don't feel like rewriting this. So we'll create a device with the specified number of shots, decorate it, return the variance of the results. Okay, so we want to do results equals circuit for in range and trials, and then we want to return the variance of the results. The variance. Oh, okay, well, we will just do the variance of the shots. Oh. We actually need to call the other function. We want to get the results. Shots, and then we want to get the, I don't understand how this is variance experiments. Return the, oh, okay, we're not actually supposed to compute the variance here. We're just supposed to compute the expectation values of the circuit however many times, and then we take the variance down here. Ooh, shots is not defined. Oh, it's n_shots. Oopsies. And trials is not defined. I misspelled it somewhere. There we go. Object of type. What the? Let's see if it lets me print anything. Oh, because it's casting it to a different object that we want. So we want to say, because up above, right, when it printed it, it was, the print has overridden the string object in this class. So when we call print, it converts it to a string, and because string _str__ is overwritten in this class, it looks like it's fine, but it's not. So we actually have to convert it to numpy. Oh, let me check. I should not print. Oh. Our variance function does not look quite right. All right, maybe I should actually read what we're supposed to do. The number of shots float. The variance. Oh. No. Oh, okay, yeah. So I should actually read the results or read the functions. Really not reading the problem. What we want to do is we want to represent this as a as an actual function. So I'm guessing that the variance decreases exponentially. right, this is an exponentially decreasing curve right here, but I don't know exactly what. I don't know the exact um, what the exact mathematical description of this is. Kind of guesstimating here. I don't know if this is the best way to do it, but this doesn't look like the scaling is right. I guess I should actually think about this rather than guessing and checking. So the variance, let's look up, I forget what the variance equation. Let's look at the variance. The variance is the description, the difference between the expectation value squared and the square of the expectation value. Okay. What's the solution to this? Oh, are we supposed to actually, so we know the expectation value is we know the expected value of x is that. I don't know how to represent this actually. The variance. Oh, okay. Well, it's a simpler circuit. I see. So we're probably gonna see what I'm thinking of here is that we're gonna represent an abstract concept of the variance of this. But I think what we want is that we're simply measuring the z. Oh, okay. So let me explain why my confusion was. I was thinking in general, what's the equation for given a number of shots, what's the variance of the expectation values of the measurement? I was thinking, I don't know how to do that. I mean that I'm too tired, it's late. I don't know how to do that. And so, but what it's really asking is what's the equation in this case? And that's probably a challenging thing in a general case. But in this case, the expected value is 0.5, or the expected value is 0 because half the time it's going to be 1, half the time it's going to be -1. And then so if we have this equation where we have the expected value of x squared minus the expected value of x squared, this part is 0 because the expected value of x is 0. However, this squared is not going to be 0 because we have on average we have 0 to 1. Is it just, yeah, so we have, right, this value is going to be the output, right? So it's going to be 0 squared, it's going to be 0.1 squared. In those cases, so, but the expectation value is not 0, right? Because it is not bounded 0 or 1 to -1. It's bounded 0 to 1 because the square, right, of -1 is 1, the square of 1 is 1. So then if we want to estimate that, then it's going to be 1 over the number of shots. There we go. Because what's going on here, right, is that as this function is a quadratic in this number of shots, and so we're taking the average, which is this expectation value, and so we're getting a inverse, so 1 over the number of shots, because this right here has gone to 0, and this is not going to 0. Well, it is. It's at an infinite number of shots because we have this representation that isn't, our shots isn't perfect. So there we go. Ooh, multi-qubit systems. We have the tensor product notation over here. Multi-qubit bases, separable operations. All right. All right, write a qubit that represents the state vector n. All right, so we want to convert this to a binary number. I don't remember this function. Let me see, convert int to binary. Let's find out what the best way to do this is. I don't remember. I do this all the time, but I forget. Okay, so we want bin, the integer. So we're going to do s equals bin of basis ID, and then we're going to do, but we want to ignore this 0b at the beginning, and then we're going to say if s of 0 equals 1, qml.poly x on wire 0, if s of 1 equals 1, qml.poly x of wires equals 1, if s of 2 equals 1. See, we just end up, if there's a 0 in this state, then we don't need to do any operation. That's why I'm not. Okay. Oh, that's why we want to do 2 right there. What's going on? I feel like something trivial was happening. Ben does give that 0b, right? Why can I not? Oh, here we go. Yeah. Oh, it's because it doesn't convert it to a constant number of bits. So what we want actually is this. We want a constant number of bits. So we want, yeah, here we go. So we actually want this 0 argument position, 0, 8 padded to the left. Dot format basis. We're just converting it to binary. That's all I'm trying to do here. Oh, but we don't want 8. We want 3. There we go. I can't change it. All right, we want to create the state. So we want to do a Hadamard on the first qubit and a poly X on the second qubit. And then we want to return QML dot expectation value of y, poly QML dot poly y, wires equals 0, and then we want to also return the z on the second one. Excellent. Now we want to create a 2-qubit observable. First, we need to prepare the state here. Notice that I'm applying an X gate on both of them to get the negative state. Now we want to create a single expectation value. All right, so let's see if that is poly X. Oh, that's right. I don't know why I did poly Z there. What do I have to do? Can I really not do a poly X gate on multiple qubits simultaneously? There's got to be a way to do that. That's so ridiculous if I can't do that. Sequence of integers. I mean, come on. This has got to be something possible. I need a multi-qubit example. Sure, we'll do noisy circuits. I bet they have. Yeah, look at this. Wires equals 0, 1. Oh, maybe. Okay. This is ridiculous. If I have to do this. Oh, okay, that is just why. I literally in the document. Look at this. How is this allowed? But you can't do poly X twice. That's very annoying. Okay, now we want to do this circuit where we do 2 observables and then the tensor product of them. So first we have qml.rx theta wires equals 0. Then we have qml.ry y2 times theta wires equals 1. Return qml.xval, qml.polyz. Really wish I could just type z. Wires equals 0. qml.xval, qml.polyz, wires equal 1. Okay. Now down here, we want the exact same code. However, we just have this @ sign here. And that should be good. Oh, we have to actually do this function. Okay, so we have to do ZZ and IZ to combine. We should do CI results times IZ results. I hope they're NumPy arrays. Yes, and the reason that was so easy is because you do this a lot in VQE, and you can just multiply them together. So we can see IZ is right here, ZI is right here, ZZ is presumably underneath this. And that's all. Next we have multi-qubit gates, but we're going to do that next time.